Right now, you are standing on a small grain of stone, roughly 8,000 miles wide. That number sounds substantial, the way most numbers do before the universe gets involved. So let's begin there, slowly, and let each scale dissolve into the next one, the way it actually does. Your own body measures somewhere around 5 or 6 feet tall. That height is the ruler your brain uses for everything. The hallway to your kitchen, the walk to the corner store, the drive across town, all of it gets processed by a brain that evolved to handle distances a human being could cover in a single day. Your ancestors needed to judge the distance to a waterhole, the length of a game trail, the width of a river crossing. Evolution built your spatial intuition for a world measured in footsteps. And tonight, that intuition is going to be retired, gently, one scale at a time. The Burj Khalifa in Dubai, the tallest building on Earth, rises 2,717 feet into the sky. Impressive by human standards, you could stack roughly 450 people head to toe and just barely match its height. Standing at its base, looking up, your neck strains and your sense of proportion already starts to wobble a little. But the Burj Khalifa is a splinter. Mount Everest rises 29,032 feet above sea level. Stack 10 Burj Khalifas on top of each other, and you still wouldn't quite reach the summit. Climbers who reach that peak describe the sensation of standing at the very edge of the Earth itself. The sky overhead deepens into indigo. The curvature of the planet becomes faintly visible. And yet this mountain, which has killed hundreds of people and broken the bodies of thousands more, barely qualifies as a wrinkle on the surface of the planet it sits on. Earth itself measures just under 8,000 miles across. If you could drive straight through the planet at highway speed, the trip would take roughly 5 days. The circumference at the equator runs about 24,900 miles. A commercial airliner cruising at 550 miles per hour would need just over 45 hours to circle the globe without stopping. That number still feels manageable. 2 days of flying, and you've circled the world. Your brain can almost hold that distance. It strains, but it holds. Now leave the surface. The International Space Station orbits roughly 250 miles up. The astronauts aboard complete a full lap of the planet every 90 minutes, circling the Earth at about 17,500 miles per hour. From up there, Earth fills most of the field of view. Continents slide past below. Hurricanes spin in white spirals over blue oceans. The planet looks enormous and alive, but the station is barely skimming the top of the atmosphere, grazing the outer edge of Earth's thin envelope of gas. If Earth were a basketball, the space station would orbit less than 1/4 of an inch above its surface. You'd need a magnifying glass just to see space at all. That's how close humanity's permanent foothold beyond the surface actually is. The moon changes everything. Earth's nearest celestial neighbor orbits at an average distance of 238,900 miles. To get a feel for that number, imagine lining up 30 Earths side by side, shoulder to shoulder, like a row of planets. The moon sits at the far end of that line. When the Apollo astronauts left Earth orbit for the moon, the trip took about 3 days. 3 days of coasting through absolute vacuum. Earth shrinking behind them, a gray cratered world, slowly growing in the window ahead. During those 3 days, those astronauts traveled farther from Earth than any human being ever had before. Radio signals between mission control and the spacecraft experienced a delay of about 1 1/3 seconds. Light itself takes that long to cross the gap between Earth and the moon. That 1 1/3 seconds is the first real crack in your intuition. You make a phone call and expect an instant reply. Conversations flow with no perceptible lag. But at the distance of the moon, the speed of light already introduces a noticeable pause. Ask a question, wait a second and a third for it to arrive, then wait another second and a third for the answer to come back. Nearly 3 seconds round trip. Annoying on a phone call, manageable, still. But this is only the moon, the nearest, most significant object to Earth. The very first rung on a ladder that climbs so high you can't yet see where it ends. The Sun sits roughly 93 million miles from Earth. Astronomers call this distance an astronomical unit, and it becomes the standard yardstick for everything else in the solar system. 93 million miles. If you could drive a car to the Sun at 60 miles per hour without stopping to refuel, eat, or sleep, the trip would take roughly 177 years. You'd need to start driving before the American Civil War, and you still wouldn't have arrived. A commercial jet would need about 19 years of continuous flight. Even light, the fastest thing in the universe, takes 8 minutes and 20 seconds to cross that gap. Every time you look at the Sun, you're seeing it as it appeared 8 minutes ago. If the Sun vanished this very instant, you'd keep seeing its light and feeling its warmth for another 8 minutes before the darkness arrived. The Sun itself is staggering on its own terms. Its diameter spans 864,000 miles. You could line up 109 Earths across its face. Its volume could hold roughly 1.3 million Earths. It accounts for 99.86% of the total mass of the entire solar system. Every planet, every moon, every asteroid, every comet, every grain of dust orbiting our star amounts to little more than a rounding error against the Sun itself. Jupiter, the largest planet, a gas giant so massive it could swallow every other planet combined, is still roughly 1,000 times less massive than the Sun. Earth is a speck of dust circling a furnace, and that furnace dominates everything within its gravitational reach. But the Sun's gravitational influence extends far beyond the planets we know. And this is where Earthbound intuition starts to genuinely collapse. Mars orbits the Sun at an average distance of 142 million miles, about 1.5 astronomical units. When Mars and Earth happen to sit on the same side of the Sun, at closest approach, the gap between them shrinks to roughly 34 million miles. Even at that minimum distance, a radio signal traveling at light speed needs more than 3 minutes to cross the void. Conversation becomes impossible. Mission controllers sending commands to a rover on Mars have to wait anywhere from 6 to 44 minutes for a round-trip response, depending on orbital positions. The rover operates largely on its own, making independent decisions, because real-time guidance from Earth is physically impossible. Distance has made the speed of light feel slow. Jupiter orbits at 5.2 astronomical units from the Sun, roughly 484 million miles out. Saturn sits at 9.5 astronomical units. These outer planets exist in a realm of cold and dim light, where sunlight has weakened considerably. At Saturn's distance, sunlight carries roughly 1/100th the intensity it has on Earth. A person standing on one of Saturn's moons would see the Sun as a bright star, not the blazing disk we know. Radio signals from the Cassini spacecraft, which orbited Saturn for years, took between 67 and 85 minutes to reach Earth. By the time an image of Saturn's rings appeared on a screen in Pasadena, the spacecraft had already traveled thousands of miles beyond the point where it had taken the picture. Uranus orbits at roughly 19 astronomical units. Neptune, the farthest known planet from the Sun, sits at about 30 astronomical units. At Neptune's distance, the Sun has shrunk down to a brilliant point of light, barely distinguishable from a very bright star. Sunlight takes over 4 hours to reach Neptune. A spacecraft traveling from Earth to Neptune, as Voyager 2 did, Took 12 years to make the trip, 12 years of flight through mostly empty space, past the gas giants and their moons, through radiation belts and magnetic fields, going ever deeper into a solar system that kept revealing just how far it actually extended beyond anything anyone could intuitively imagine. The Voyager missions reshaped humanity's sense of cosmic proportion entirely. Launched in September 1977, Voyager 1 has been traveling for more than 48 years, and as of early 2026, sits roughly 165 astronomical units from the Sun. That's over 15 billion miles. Voyager 1 is the farthest human-made object that exists. It crossed the boundary of the heliosphere, that bubble of charged particles the Sun projects into space, back in August 2012, becoming the first human-made object to enter true interstellar space. 15 billion miles sounds like the edge of everything. It isn't remotely close to the edge of anything. The Oort cloud marks the true outer boundary of the Sun's gravitational influence. This theoretical shell of icy bodies is thought to surround the solar system in a roughly spherical halo, extending from about 2,000 astronomical units out to perhaps 100,000 astronomical units from the Sun. 100,000 astronomical units is roughly 1.6 light-years. The Oort cloud is so far away that objects out there take millions of years to complete a single orbit around the Sun. Comets that fall in from this distant reservoir, swinging past Earth on long elliptical paths, might not return for tens of thousands, or even millions, of years. At Voyager 1's current speed of roughly 38,000 miles per hour, it would take the spacecraft about 500 years just to reach the inner edge of the Oort cloud. It would take roughly 30,000 years to fully cross the cloud and emerge on the other side. 30,000 years. Human civilization, as we generally understand it, is about 10,000 years old. Voyager would need 3 times the entire span of recorded human history just to cross a single structure within our own solar system. And yet, at 1.6 light-years across, the Oort cloud represents only a fraction of the distance separating us from the nearest star. The nearest star to our own Sun is Proxima Centauri, a dim red dwarf, sitting 4.24 light-years away. That means light itself, traveling at 670 million miles per hour, needs more than 4 years to cross that gap. Voyager 1, our fastest spacecraft, traveling at its current speed, would need roughly 73,000 years to reach Proxima Centauri, if it were even heading in that direction. 73,000 years. The last ice age ended roughly 11,700 years ago. Voyager would need to travel a distance equivalent to more than 6 ice ages laid end to end, just to reach the nearest star. Think about what that distance actually means in physical terms. If you shrank the Sun down to the size of a golf ball and set it on a table in front of you, Earth would be a fine grain of sand orbiting roughly 15 feet away. Jupiter would be a small pea orbiting about 75 feet out. Neptune, a slightly smaller pea, would orbit at roughly 450 feet. The Oort cloud would stretch out roughly 300 miles in every direction, a gravitational territory the size of a small state, surrounding a single golf ball. And Proxima Centauri, the next nearest golf ball, would sit roughly 4,800 miles away. 4,800 miles of absolute emptiness between 2 tiny spheres. That is the interstellar neighborhood. That is the actual distance separating stars. This emptiness defines the true nature of the solar system. Planets give the impression of a crowded family when drawn in textbook diagrams, neatly spaced along colorful orbital lines. Those diagrams are lies. They compress distances by factors of thousands just to fit on a page. In reality, the solar system is almost entirely empty space. If you threw a dart randomly into the volume bounded by Neptune's orbit, the odds of hitting anything at all, a planet, a moon, an asteroid, would be so vanishingly small as to be effectively zero. Space is empty, deeply, relentlessly, almost insultingly empty. The objects within it are scattered points inside a void so vast that calling it large undersells the point entirely. New Horizons, which flew past Pluto in July of 2015, offered a striking demonstration of this emptiness. After its encounter with Pluto, roughly 33 astronomical units from the Sun, New Horizons continued outward into the Kuiper Belt, the region of icy bodies beyond Neptune. In January 2019, it flew past Arrokoth, a small contact binary object, sitting roughly 44 astronomical units out. Beyond Arrokoth, New Horizons continues flying through increasingly empty space. Its instruments detect only the faintest whispers of solar wind particles and cosmic dust grains. The environment is about as close to perfect nothingness as nature allows. Temperatures hover just a few dozen degrees above absolute zero. Sunlight has faded down to a pale point, barely brighter than the surrounding stars. The spacecraft is utterly alone, surrounded by trillions of cubic miles of nothing. This solitude carries a quantitative dimension worth sitting with. The average density of matter within the solar system, if you spread the mass of every planet, moon, asteroid, and comet evenly across the volume bounded by the Oort cloud, comes out extraordinarily close to a perfect vacuum. The Sun holds almost all the mass, and occupies only a vanishingly small fraction of the total volume. Everything else is space. Not metaphorical space, actual, three-dimensional physical emptiness, stretching in every direction for billions of miles. This is the solar system. This represents everything humanity has ever physically explored, touched, or visited by machine. Every Apollo mission, every Mars rover, every flyby of Jupiter, Saturn, and Pluto, all of it happened within the gravitational territory of this single star. No human-made object has ever reached another star. Not a single signal we've sent has had time to travel to our nearest stellar neighbor and return. We are confined to one tiny island in an ocean so vast that the nearest neighboring island requires a journey of tens of thousands of years at our current fastest speed. And here's the detail that completely dismantles the first layer of intuition. The solar system, from the Sun out to the edges of the Oort cloud, spans roughly 3 light-years in diameter. The Milky Way galaxy, the structure that contains the solar system, spans roughly 100,000 to 200,000 light-years across, depending on how you measure it. That means the galaxy is, at minimum, 30,000 times wider than our entire solar system. Everything we've ever explored, every planet we've photographed, every comet we've tracked, every void we've crossed, fits inside a structure at least 30,000 times larger. If the solar system were a single grain of salt, the Milky Way would stretch across an entire regulation basketball court and beyond. We haven't even begun talking about what lies beyond the galaxy yet. The solar system is simply the smallest unit of measurement on the scale we're about to climb. Every distance you've struggled to grasp so far, the 93 million miles to the Sun, the billions of miles to Neptune, the trillions of miles to the Oort cloud, collapses to a single invisible point. Once you step back far enough, the numbers are about to grow so large that distances within our own solar system will become entirely imperceptible. Not approximately zero. Functionally, meaningfully, definitively zero. Voyager 1 has been flying for nearly half a century. It has traveled farther than any object humanity has ever built. It carries a golden record containing sounds and images of Earth, a message in a bottle, tossed into a cosmic ocean, and after 48 years of relentless travel at 38,000 miles per hour, it has covered less than 0.1% of the distance to the nearest star. That is where we currently stand. That is the entire sum of humanity's physical reach into the cosmos, a fraction so small it vanishes when you round to the first decimal place. The next step takes us across a gulf that makes the entire solar system disappear. The distance separating our solar system from the nearest star is not a distance your brain was built to process. 4.24 light-years to Proxima Centauri. The words slide by easily enough, because they sound like an ordinary measurement, a number followed by a unit. But it's that unit, the light-year, doing all the heavy lifting, and your mind lets it pass without question. 1 light-year equals roughly 5.88 trillion miles. Multiply that by 4.24, and the distance to Proxima Centauri comes out to roughly 25 trillion miles. Written out in full, that number is almost tedious just to say 25, followed by 12 zeros. And this is the nearest star, the closest point of nuclear fire in our entire stellar neighborhood. Everything else is farther. The interstellar medium between here and there isn't the same kind of emptiness found between planets. It's emptier. Within the solar system, the solar wind fills space with charged particles, a thin plasma that thins with distance, but never fully disappears before reaching the heliopause. Beyond that boundary, interstellar space contains roughly 1 atom per cubic centimeter. For comparison, the air you're breathing right now contains roughly 25 quintillion molecules per cubic centimeter. The difference between those two numbers is so extreme that interstellar space constitutes a more thorough vacuum than anything ever produced in a laboratory on Earth. If you stood unprotected in that void, you wouldn't be surrounded by darkness. You'd be surrounded by nothing. The space between stars is about as close to a true vacuum as nature gets. And yet, that vacuum isn't entirely featureless. Vast clouds of molecular hydrogen drift between the stars, some stretching tens of light-years across. These molecular clouds are stellar nurseries, regions where gas slowly accumulates under its own gravity until pockets collapse, heat up, and ignite nuclear fusion. Every star you've ever seen in the night sky was born inside one of these clouds. The Sun itself formed roughly 4.6 billion years ago, from a collapsing region within a molecular cloud that no longer exists. The matter that became Earth, that became you, was once scattered through interstellar space as atoms of hydrogen, helium, carbon, oxygen, and iron, drifting through the void between older stars that had already lived and died. This is one of those facts that sounds poetic, but happens to be literally true. The iron flowing through your blood was forged in the heart of a massive star that exploded as a supernova billions of years before the solar system formed. The calcium in your bones was produced by a different kind of stellar explosion. The oxygen you're breathing was fused inside the furnace of yet another star. You aren't metaphorically made of stardust. You are materially, chemically, atomically built from elements manufactured inside stars and ejected into interstellar space by violent deaths. The space between stars isn't simply empty. It's the mechanism by which the raw materials of planets and people get transported across light-years and billions of years of cosmic time. But the 400 billion stars in our galaxy are far from identical, and the diversity hiding within that population is staggering. The Sun is a yellow dwarf, a middle-aged middle-temperature, middle-luminosity star that will burn steadily for roughly 10 billion years before swelling into a red giant and eventually collapsing into an Earth-sized white dwarf. It is the most ordinary kind of star imaginable, nothing remarkable on a cosmic scale. and it represents only one narrow category among many. Red dwarfs are the most common stars in the Milky Way, making up roughly 70 to 75% of the entire stellar population. They're small, dim, and cool compared to the Sun, with surface temperatures ranging from about 3,000 to 4,000 degrees Kelvin. The smallest red dwarfs contain only about 8% of the Sun's mass, barely enough to sustain hydrogen fusion in their cores. Whatever they lack in brilliance, they make up for in longevity. A red dwarf burns its fuel so slowly it can shine for trillions of years, far longer than the current age of the universe. Every red dwarf that has ever ignited is still burning today. None has yet had time to die. These pale, patient stars are the most numerous objects in the galaxy, and yet almost none are visible to the naked eye from Earth. The night sky you see is dominated by rare, luminous giants. The true population of the galaxy hides in the dark. At the opposite extreme sit blue supergiants, stars so massive and so hot that they burn through their nuclear fuel in just a few million years. A blue supergiant can carry 50 or even 100 times the mass of the Sun, with surface temperatures exceeding 30,000 degrees Kelvin. Their luminosity outshines the Sun by hundreds of thousands of times. A single blue supergiant can produce more energy per second than an entire cluster of red dwarfs generates in a year, but their ferocity is their undoing. These stars live fast, fusing progressively heavier elements in their cores until they reach iron, at which point nuclear fusion can no longer hold back gravitational collapse. The core implodes. The outer layers blast outward in a supernova explosion that can briefly outshine an entire galaxy. What's left behind depends on mass. Some leave behind neutron stars, objects so dense that a single teaspoon of their material would weigh roughly 6 billion tons at Earth's surface. The most massive leave behind black holes, regions of space-time where gravity has triumphed so completely that nothing, not even light, can escape. Neutron stars rank among the most extreme objects in the galaxy. They pack roughly 1.5 times the Sun's mass into a sphere only about 12 miles across. Their density exceeds water's by a factor of more than 100 trillion. Their surfaces are covered in a crystalline lattice of iron nuclei, compressed so tightly that the material is harder than anything on Earth. Some neutron stars spin hundreds of times per second, sweeping beams of radiation across space like cosmic lighthouses. These are pulsars, and their signals are so precise they rival atomic clocks in accuracy. Others carry magnetic fields 1 trillion times stronger than Earth's, powerful enough to wipe the data off a credit card from roughly 100,000 miles away, about a quarter of the distance to the Moon. These magnetars occasionally release bursts of energy so intense that a single flare can compress Earth's magnetosphere from tens of thousands of light-years away. The Milky Way contains somewhere between 100 million and 1 billion neutron stars, and perhaps 100 million stellar mass black holes, all remnants of massive stars that lived and died across the galaxy's 13 billion year history. These corpses drift through the galactic disk and halo, invisible except when they interact with surrounding matter or reveal themselves through gravitational effects. You could pass within a few light-years of a black hole and never even know it. Between the extremes of red dwarfs and blue supergiants lies a vast spectrum of stellar types, each with its own mass, temperature, luminosity, and lifespan. Orange dwarfs run slightly cooler than the Sun. White main-sequence stars run slightly hotter. Red giants have exhausted the hydrogen in their core and swollen to hundreds of times the Sun's diameter. Asymptotic giant branch stars shed their outer layers to form planetary nebulae, glowing shells of gas that drift into interstellar space, contributing raw material to future generations of stars. The galaxy is a recycling machine. Stars form from gas, burn for millions or billions of years, eject enriched material into space when they die, and that material gets gravitationally gathered again to form the next generation. Each successive generation of stars carries slightly more heavy elements than the one before, gradually enriching the galaxy's chemical inventory over cosmic time. This enrichment is what makes planets like Earth possible at all. The first generation of stars, formed from the nearly pure hydrogen and helium left over from the Big Bang, couldn't have hosted rocky worlds, because the heavy elements needed to build rock, iron and silicon and oxygen, didn't yet exist in meaningful quantities. It took billions of years of stellar nucleosynthesis, billions of years of supernova and stellar winds scattering heavy elements through interstellar space, before the galaxy's chemical composition grew rich enough to produce the kind of planet capable of supporting complex chemistry and eventually life. Earth is a late. Earth is a later of Grandi, Urchurate, Birch of Gisapat up, Erst Verat, Ergst, Ik, Cap, S, Plex, Et, Ban, Ekapa, with Epia, with a piece of pepper, spice welcome with Lissa, Ax, Wakat, at Slab, Pep, outward at Aka, at that about, Copper, Apple, Wapa, or Pepper, Okpa, at Warlock, Askus, Muskus, Wevella, Cast, picked up with double wet, the scatter, and winds roots to the Wicketour, Syndicalist, It exists because generations of stars lived and died before the sun was ever born. And this leads to one of the most profound revelations of modern astronomy. Planets aren't rare curiosities, they're everywhere. The Kepler Space Telescope, which operated from 2009 to 2018, detected more than 2,700 confirmed exoplanets and identified thousands more candidates by watching the brightness of over 150,000 stars, looking for the tiny dips in light caused by planets passing in front of their host stars. Statistical analysis of Kepler's data led to a remarkable conclusion. On average, every star in the Milky Way hosts at least one planet. Many host several. Rocky planets sitting within the habitable zone, that orbital region where liquid water could persist on a planet's surface, aren't rare exceptions. Their number could run into the tens of billions in our galaxy alone. The James Webb Space Telescope has begun examining the atmospheres of some of these worlds, searching for chemical signatures that might indicate habitability or even biological activity. Water vapor, carbon dioxide, and methane have already been detected in the atmospheres of several exoplanets. Detecting biosignature gases, combinations of atmospheric chemicals difficult to explain without biological processes, remains the next great challenge. If such a detection were made, it would confirm that the Milky Way isn't just a galaxy of 400 billion stars, with tens of billions of rocky planets. It would be a galaxy where life arose independently on multiple worlds. The scale of a galaxy isn't only about distance and star count. It's a measure of possibility. Every additional star represents another furnace. Every furnace can warm another world. Every world is another chemistry experiment that's been running for billions of years. 400 billion experiments scattered across 200,000 light-years of space, operating for as long as 13 billion years. The number of experiments the galaxy has run on the chemistry of life is so large that the real question isn't whether the right conditions exist elsewhere. The question is how many times those conditions have actually produced a result. Now, widen your view. The Sun is one star among roughly 400 billion that make up the Milky Way galaxy. That figure isn't precise, because vast portions of the galaxy are hidden behind thick clouds of dust that block visible light. But modern infrared surveys and statistical modeling converge on an estimate somewhere between 100 and 400 billion stars, with the most recent analyses favoring the upper end. Each of these stars has its own gravitational territory, its own potential retinue of planets, moons, and comets. Some exist alone, like our Sun. Others exist as binary or triple systems, 2 or 3 stars bound by gravity, orbiting a common center of mass. A significant fraction, perhaps the majority, host at least one planet. 400 billion stars spread across a structure between 100,000 and 200,000 light-years in diameter. The traditionally cited figure in textbooks was 100,000 light-years, but research over the past decade, using stellar streams and halo star surveys, has revised that estimate considerably upward. The bright disk of stars, the glowing spiral structure you see in every artist's rendering, spans roughly 100,000 light-years, but the galaxy doesn't end where the bright stars thin out. Fainter, stellar populations extend well beyond the visible disk, and the dark matter halo, the invisible gravitational scaffolding holding everything together, extends to at least 250,000 light-years, and possibly much farther. The Milky Way's sphere of gravitational influence is significantly larger than the luminous disk most people picture when they hear the word galaxy. The disk itself is remarkably thin compared to its width. The stellar disk measures roughly 2,000 light-years thick at the Sun's position, though it flares and thickens near the center. The ratio of diameter to thickness makes the Milky Way proportionally flatter than a compact disk. If you shrank the galaxy down to the diameter of a dinner plate, the disk would be thinner than a sheet of paper. This extreme flatness results from the galaxy's rotation. Just as pizza dough flattens when spun, the rotating mass of the galaxy settled, over billions of years, into a thin plane where most of the stars, gas, and dust concentrate. The Sun orbits the galactic center at a distance of roughly 26,000 light-years, placing us roughly halfway between the core and the outer edge of the visible disk. We sit within one of the galaxy's spiral arms, specifically a structure called the Orion Arm or local spur, which branches off between the larger Perseus Arm and the Sagittarius Arm. Our position isn't special or central, it's a suburb. We live in a quiet galactic neighborhood that's neither the dense urban core nor the sparse rural edge, but somewhere comfortably in between. A peaceful district where stars sit a few light-years apart, and the night sky holds enough visible stars to inspire wonder without overwhelming the senses. The galactic center, by contrast, is a place of terrifying density and violence. Stars near the core are packed thousands of times more tightly than in our own cosmic neighborhood. If Earth orbited a star near the galactic center, the night sky would blaze with so many bright stars that true darkness would never fall. You could read a book by starlight alone, but that beauty would come with danger. Stellar encounters would be far more frequent. Gravitational perturbations could destabilize planetary orbits, and radiation from nearby supernova and the central black hole would bathe everything in lethal energy. At the very heart of the Milky Way sits Sagittarius A*, a supermassive black hole, roughly 4 million times the mass of our Sun. This object has been confirmed through decades of careful observation. Astronomers have tracked individual stars orbiting the galactic center and measured their trajectories with extraordinary precision. One star, designated S2, completes a full orbit around Sagittarius A** every 16 years, reaching speeds of roughly 2.5% of light speed at its closest approach. The only object massive and compact enough to produce such orbital speeds without being visible is a black hole. In 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A*, showing the glowing ring of superheated gas swirling around the black hole's shadow. The image confirmed what decades of indirect evidence had already established. A monster lives at the heart of our galaxy. Despite its enormous mass, Sagittarius A* is surprisingly quiet compared to supermassive black holes in other galaxies. Some galactic centers are active, blasting persistent jets of matter thousands of light-years into space, outshining every star in their host galaxy combined. Sagittarius A* is dormant, currently consuming very little matter, but it hasn't always been calm. Observations of structures called the Fermi bubbles, enormous lobes of high-energy gas extending above and below the galactic plane, suggests Sagittarius A* experienced a period of intense activity several million years ago, producing outbursts that sculpted the distribution of gas across tens of thousands of light-years. The monster sleeps. It hasn't always slept. The galaxy rotates, but not like a solid wheel. Stars at different distances from the center orbit at different speeds, in a pattern called differential rotation. The Sun moves around the galactic center at roughly 515,000 miles per hour. Even at that extraordinary speed, a complete orbit takes roughly 230 million years. Astronomers call this period a galactic year. The last time the Sun was in its current orbital position, dinosaurs hadn't yet appeared on Earth. Before that, the most complex life form on the planet was a fish. Across the 4.6 billion year history of the solar system, the Sun has completed only about 20 galactic orbits. The galaxy operates on timescales that make geological eras look brief. Differential rotation creates the spiral arms that give the Milky Way its signature appearance. These arms aren't permanent structures made of the same stars. They're density waves, regions where stars and gas temporarily bunch together before moving on. The same way cars slow down and cluster in a traffic jam, even though they eventually pass through individually. Stars spend part of their orbit inside an arm and part between arms. The spiral structure persists because the density wave itself rotates at a different speed than the stars, maintaining its spiral shape for billions of years, even as individual stars pass through it. New stars tend to form preferentially within the arms, because of the higher gas density that collapses under gravity there. That's why spiral arms glow brighter than the space between them. They're studded with young, hot, luminous stars, along with the nebulae from which those stars recently formed. Beyond the bright disk, the galaxy carries a vast spherical halo populated by ancient stars, globular clusters, and enormous quantities of dark matter. Globular clusters are dense, spherical groupings of hundreds of thousands, sometimes millions, of stars bound together by mutual gravity. The Milky Way hosts roughly 150 known globular clusters, many orbiting well above and below the galactic plane, tracing paths through the halo that revealed the galaxy's total gravitational mass. These clusters rank among the oldest objects in the galaxy, with ages reaching 12 to 13 billion years. They formed when the universe itself was young, before the Milky Way had taken its current shape. Stellar streams also wind through the halo, and these ghostly rivers of stars have revolutionized our understanding of how far the galaxy actually extends. Stellar streams form when the Milky Way's gravity captures and tears apart smaller galaxies or globular clusters that venture too close. The captured stars stretch into long, thin filaments that orbit through the halo for billions of years before fully dispersing. The Sagittarius stream is the most striking example, wrapping multiple times around the entire galaxy like ribbon wound around a spool. Mapping these streams reveals the gravitational field they travel through, and that field extends well beyond the visible disk. Stars in the most distant known galactic streams orbit at distances exceeding 200,000 light-years from the galactic center. Their presence proves that the Milky Way's gravitational influence, and therefore its true physical extent, reaches at least that far. Dark matter makes all of this possible. Roughly 85% of the Milky Way's total mass consists of dark matter, a substance that doesn't emit, absorb, or interact with light in any detectable way. Its presence is inferred entirely through gravitational effects. Stars in the outer galaxy orbit faster than their visible mass alone should allow. Without the additional gravitational pull from a massive halo of invisible matter, those outer stars would simply fly off into intergalactic space. Dark matter provides the missing gravity. It forms a spherical halo that extends well beyond the luminous disk, wrapping the entire galaxy in an invisible gravitational cocoon. Estimates place the Milky Way's total mass at roughly 1.5 trillion solar masses, with the overwhelming majority of that mass residing in the dark matter halo rather than in stars or gas. The bright, beautiful galaxy you see in photographs is the visible icing on an invisible cake that outweighs it by a factor of 10. This means that when astronomers talk about the size of the Milky Way, the answer depends on what's being measured. The luminous disk spans roughly 100,000 light-years. The known stellar halo extends beyond 200,000 light-years. The dark matter halo might reach 300,000 light-years or more. The sphere of gravitational influence, the region within which objects remain bound to the galaxy, extends to perhaps 500,000 or even 1,000,000 light-years, depending on the model used. Including the full dark matter halo, the Milky Way isn't a flat disk at all. It's a vast, roughly spherical structure with a thin, bright disk at its center, and its true radius is far larger than the visible portion that fills every astronomy poster. Recent discoveries have reinforced this expanded picture. The Gaia Space Observatory, launched by the European Space Agency in 2013, has precisely measured the positions and motions of nearly 2 billion Milky Way stars. This unprecedented dataset has revealed previously unknown stellar streams, mapped the three-dimensional structure of the spiral arms with new clarity, and confirmed that the galactic disk is warped, curving upward on one side and downward on the other, like a footprint pressed into it. This warp may result from gravitational interactions with the Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way, roughly 160,000 light-years away. Even at that distance, the Large Magellanic Cloud's gravitational pull is strong enough to distort the shape of the galactic disk, demonstrating that the Milky Way doesn't exist in isolation, but is constantly influenced by its gravitational neighbors. The Large and Small Magellanic Clouds are the two most prominent satellite galaxies, visible to the naked eye from the southern hemisphere as diffuse glowing patches. But the Milky Way has at least 60 known satellite galaxies, and fainter ones continue to be discovered in deep surveys. Most are tiny dwarf galaxies containing only a few million stars, but their orbits reveal the total gravitational mass they're responding to. Tracking these satellites, and the trails they leave behind, has become one of the most effective methods for measuring the Milky Way's full mass and extent. Every newly discovered satellite pushes the known boundary of the galaxy's gravitational reach a little farther. The Milky Way is itself a cannibal. It grows by absorbing smaller galaxies that venture too close. The Sagittarius dwarf elliptical galaxy is currently being devoured. It has already stretched into a long stream of stars wrapping around the galactic halo, and within a few 100 million years it will lose its identity entirely, its stars absorbed into the broader Milky Way population. This isn't a rare event. Forensic analysis of the Milky Way's stellar populations, using chemical signatures and orbital data, has revealed evidence of multiple past mergers. The largest known event is the Gaia-Enceladus merger, which occurred roughly 10 billion years ago, when a galaxy with a mass roughly a quarter that of the Milky Way collided with our own and merged. The remnants of that ancient galaxy are detectable today as a distinct population of halo stars, with chemical compositions and orbital characteristics different from stars born natively in the Milky Way. Our galaxy was built across billions of years of gravitational accumulation and the violent consumption of smaller systems. All of this together, the 400 billion stars, the spiral arms, the central black hole, the stellar streams, the dark matter halo, the satellite galaxies being absorbed, the ancient remnants of past mergers, constitutes a single galaxy. One structure among an estimated 2 trillion in the observable universe. Every fact you've just absorbed about the Milky Way, every distance, every mass, every timescale, applies with similar or greater scale to each of those 2 trillion other galaxies. Some are smaller than ours, many are comparable. A significant number are far larger, containing 1 trillion stars or more, hosting supermassive black holes with masses billions of times that of our Sun. The nearest major galaxy comparable to the Milky Way is Andromeda, sitting roughly 2.5 million light-years away. This distance deserves to be fully absorbed. The light leaving Andromeda tonight began its journey 2.5 million years ago, when the ancestors of modern humans were just beginning to use stone tools on the plains of Africa. Every photon from Andromeda entering your eye right now carries information that old you aren't seeing Andromeda as it exists now. You're seeing a ghost, an image preserved in ancient light, a portrait of a galaxy as it appeared before your species existed. The distance to our nearest large neighbor is roughly 2.5 million light-years, about 10 times the diameter of the Milky Way itself. The space between our galaxy and Andromeda is a gulf so immense that the entire Milky Way, its 200,000 light-years of gravitational territory, its 400 billion stars, its 1.5 trillion solar masses of visible and invisible matter, could be placed inside that gap 12 times over, with room left to spare. This space is overwhelmingly empty. A handful of faint dwarf galaxies drift through it. Wisps of intergalactic gas occupy the space at densities even lower than the interstellar medium. In this intergalactic void, temperatures hover near the cosmic background level, just a few degrees above absolute zero. This is the true desert of the cosmos, not the space between planets, not the space between stars, but the space between galaxies. A void so deep and so empty that light takes millions of years to cross it, even at the maximum speed the universe allows. And yet Andromeda is practically next door. It belongs to the same small gravitational family as the Milky Way, a collection called the local group. Beyond the local group, the next comparable cluster of galaxies sits tens of millions of light-years away. Beyond that, hundreds of millions. Beyond that, billions. Each step outward multiplies the distance by factors so large that the previous scale becomes meaningless. The Milky Way, this colossal structure whose description has occupied the entirety of our journey so far, a galaxy so vast that light needs 200,000 years to cross it, so massive that billions of solar masses of matter hold it together, so ancient that its oldest stars formed when the universe was only 1 billion years old, is about to shrink down to a single point of light in the next cosmic image. Everything we've discussed so far, the solar system, the interstellar void, the spiral arms, the galactic halo, reduces to a single point among billions. At the next scale up, the Milky Way appears the way Earth appeared from the edges of the solar system, small, getting smaller, and far from finished, shrinking. Andromeda is falling toward us. It isn't drifting, it isn't wandering, it's falling. The Milky Way and Andromeda are locked in a mutual gravitational embrace that has been pulling them toward each other for billions of years. Andromeda approaches at roughly 250,000 miles per hour, closing the 2.5 million light-year gap with the patience of cosmic time. In roughly 4 to 5 billion years, the two galaxies will collide. Their spiral arms will deform. Their dark matter halos will interpenetrate. Hundreds of billions of stars will reorganize over the course of 1 billion years into a single massive elliptical galaxy astronomers have already, half-jokingly, named Milky Way. The collision sounds catastrophic, but individual stars are so far apart from each other that direct stellar impacts will be extremely rare. The Sun, if it still exists by then, will likely survive the merger with its planets intact, flung onto a new orbit around the combined galactic center. The violence of a galaxy collision is gravitational, not physical. It reshapes structure without destroying components. But the collision between the Milky Way and Andromeda is a local affair, a private gravitational drama between two neighbors. To understand the true scale of what surrounds us, we need to step back far enough that this looming collision between two galaxies containing a combined total of roughly 1 trillion stars becomes a minor event, barely worth noting on the larger cosmic stage. The Milky Way and Andromeda are the two dominant members of a gravitational family called the Coaxial Group. This collection includes more than 80 known galaxies, spread across a volume roughly 10 million light-years in diameter. Most members are dwarf galaxies, small faint collections of a few billion or even a few million stars each. The Triangulum Galaxy, also called Messier 33, is the third largest member, containing roughly 40 billion stars and sitting about 3 million light-years from the Milky Way. Everything else in the local group is considerably smaller. The Large Magellanic Cloud contains perhaps 30 billion stars. The Small Magellanic Cloud, 7 billion. Many of these dwarf satellite galaxies contain so few stars that they weren't discovered until deep sky surveys revealed them, hidden in the glare of the Milky Way. The local group is gravitationally bound. Despite the expansion of the universe pulling distant objects apart, the galaxies of the local group are close enough and massive enough that their mutual gravity overcomes that expansion. They orbit a common center of mass somewhere between the Milky Way and Andromeda, bound together for a predictable cosmic future. This gravitational binding is what distinguishes a true group of galaxies from a random scattering of galaxies that simply happen to sit near each other. The local group is a real physical structure, a cosmic home where the members are permanently bound. 10 million light-years across 80 galaxies. That sounds like a substantial community, until you discover what's hiding just beyond the neighborhood. The Virgo cluster sits roughly 54 million light-years from the local group. It contains more than 1,300 known galaxies, concentrated in a volume roughly 15 million light-years across. At its heart sits Messier 87, a giant elliptical galaxy hosting a supermassive black hole with a mass of 6.5 billion suns, more than 1,000 times the mass of the black hole at the Milky Way center. In 2019, the Event Horizon Telescope produced the first direct image of a black hole, using the monster at the heart of Messier 87 as its target, capturing the glowing ring of superheated plasma swirling around its shadow. That image traveled 54 million light-years to reach us, which means the light was emitted when the early ancestors of modern horses were just beginning to appear on Earth. The Virgo cluster isn't just larger than the local group, it represents a fundamentally different category of structure. Galaxy clusters are the most massive gravitationally bound objects in the universe. They contain not only hundreds or thousands of individual galaxies, but vast quantities of superheated gas, called the intracluster medium. This gas, heated to tens of millions of degrees by the gravitational energy of the cluster's formation, glows in X-ray wavelengths and actually contains more mass than all the stars in all the cluster's galaxies combined. The visible galaxies are islands floating in an invisible ocean of hot plasma, and surrounding all of it, dominating everything else by a factor of roughly 5-to-1, sits the cluster's dark matter halo. When astronomers add up the Virgo cluster's total mass, galaxies, hot gas, and dark matter combined, the figure reaches roughly 1.2 quadrillion solar masses. That's 1.2 times 10 to the 15th power suns, a number that has stopped meaning anything to the human brain. The local group itself is falling toward the Virgo cluster. Our entire galactic neighborhood, more than 80 galaxies, is being pulled toward Virgo at roughly 250 miles per second. We will never arrive. The expansion of the universe is carrying the Virgo cluster away from us slightly faster than we're closing the gap. So the distance between us and Virgo slowly widens despite our efforts to approach it. But the Virgo cluster's gravitational influence is real and measurable. It distorts the motion of every galaxy in our region of space, adding a systematic velocity component that astronomers must carefully subtract when measuring cosmic expansion rates. Before leaving the immediate vicinity of the local group, let's pause on the gulf separating us from the Virgo cluster minus 54 million light-years of intergalactic space. This isn't simply the interstellar void scaled up. It's a qualitatively different kind of emptiness, and it deserves to be examined on its own terms. Between galaxies, matter density drops to levels that make interstellar space look crowded by comparison. The intergalactic medium present in the voids between galaxy groups contains roughly 1 to 10 atoms per cubic meter, not per cubic centimeter, per cubic meter. The air in the room where you're sitting contains roughly 25 sextillion molecules per cubic meter. The Milky Way's interstellar medium contains roughly 1 million atoms per cubic meter. Intergalactic space is 1 million times emptier still. If you could somehow teleport to a random point in the gulf between the local group and the Virgo cluster, you'd be floating in a vacuum more perfect than anything any laboratory on Earth has ever achieved, or likely ever will. The temperature would sit just above the cosmic background level of 2.7 degrees Kelvin, barely above absolute zero. No star would be close enough to warm you. No galaxy would be close enough to see with the naked eye, except as a faint, indelible smudge. The darkness would be absolute. The silence would be total. The isolation would be complete. This void isn't merely the space between interesting objects. It's the dominant physical reality of the universe. If you placed a pin at random anywhere on a map of the cosmos, the overwhelming probability is that it would land in intergalactic space, not inside a galaxy. The universe is mostly empty. Galaxies are exceptions, rare condensations of matter floating in an ocean of almost nothing. We live inside one of these exceptions, which gives us a deeply misleading sense of how full the universe actually is. Even at its emptiest, the night sky is rich with light, compared to the true average state of the cosmos. Now consider what it means to cross that void. Light, the fastest thing in the universe, takes 54 million years to travel from the Virgo cluster to the local group. When that light departed, the Indian subcontinent was still crashing into Asia, slowly pushing up the first foothills of the Himalayas. Whales had only just begun evolving from land-dwelling ancestors. The entire history of the human lineage, every hominid species, every stone tool, every written word, every war, every symphony, every scientific theory, fits inside less than 1% of that light's travel time. The intergalactic gulf isn't measured in human time. It's measured in evolutionary time, in geological time, on scales so vast that entire branches of the tree of life grow, flourish, and go extinct, while a single photon crosses from one galaxy cluster to another. The Virgo cluster deserves a closer look on its own, because galaxy clusters aren't simply collections of galaxies. They're the most massive gravitationally bound objects in the universe, and they function as physical systems with their own internal dynamics, their own weather, their own dark matter architecture. A galaxy cluster is held together by gravity, but the gravitational well is overwhelmingly dominated by dark matter. In a typical cluster, dark matter accounts for roughly 80% of the total mass. The hot intracluster gas contributes roughly 15%. The galaxies themselves, the bright objects that give the cluster its visual identity, account for only about 5% of its mass. The galaxies are decoration. Dark matter is the structure. This ratio has been confirmed repeatedly through multiple independent methods, and it constitutes one of the most compelling arguments for dark matter's existence in observational cosmology. Gravitational lensing provides the most dramatic visual proof. When light from a distant galaxy passes near a massive cluster, the cluster's gravity bends it, distorting and magnifying the images of background galaxies. In some cases, the distortion produces arcs, rings, or multiple images of the same background galaxy, arranged symmetrically around the cluster. The degree of distortion reveals the total mass responsible for the bending. When astronomers calculate the mass needed to produce the observed lensing effects, they consistently find it far exceeds the mass of the visible galaxies, and the hot gas can't account for the missing mass either. This is dark matter. The bullet cluster, sitting roughly 3.8 billion light-years from Earth, provides what many physicists consider the most compelling direct evidence for dark matter's existence. This system consists of two galaxy clusters that collided at roughly 10 million miles per hour. During the collision, the hot gas from each cluster, which interacts electromagnetically, collided and slowed, piling up between the two clusters. This gas is visible in X-rays as a bright concentration between the clusters, but gravitational lensing maps reveal that the majority of each cluster's mass passed through the collision without slowing down at all. The dark matter components of both clusters, which interact only through gravity, passed through each other like ghosts. The result is a system where visible mass and gravitational mass are spatially separated, gas in the middle, dark matter on the outside. This separation is nearly impossible to explain without invoking some form of matter that interacts with ordinary matter only through gravity. The bullet cluster is dark matter's fingerprint, caught in the act. The hot gas filling galaxy clusters is itself a remarkable substance, reaching temperatures of 100 million degrees, far exceeding the core temperatures of most stars. At those temperatures, atoms are completely ionized, stripped of all their electrons, forming a plasma that glows brightly in X-ray wavelengths. This intracluster medium isn't a minor component. It contains more ordinary matter than every star and every galaxy in the cluster combined. Galaxies contribute most of the light. Gas contributes most of the ordinary matter. Neither dominates the gravitational balance sheet. Dark matter does that. X-ray observatories like Chandra and XMM Newton have mapped the distribution of this hot gas across dozens of galaxy clusters, revealing complex structures, including shock fronts wherein falling matter collides with existing gas, cold fronts where dense gas cores oscillate within the cluster's gravitational potential, and cavities carved out by jets from supermassive black holes at the centers of the largest cluster galaxies. These central galaxies, called brightest cluster galaxies, are the most massive galaxies in the universe, containing up to several trillion stars and hosting supermassive black holes with masses reaching tens of billions of suns. Jets from these black holes can extend hundreds of thousands of light-years into the surrounding medium, injecting enormous amounts of energy into the intracluster gas and preventing it from cooling and collapsing into new stars. Widening the view further, both the local group and the Virgo cluster sit within a much larger structure called the Laniakea supercluster, identified and named in 2014 by a team led by astronomer Brent Tully. Laniakea spans roughly 500 million light-years and contains the mass of roughly 100 quadrillion suns, spread across about 100,000 galaxies. The name, of Hawaiian origin, means immense heaven, which turns out to be a slight understatement. Laniakea was mapped not by counting galaxies, but by tracking their motions. Every galaxy in the universe carries a peculiar velocity, a motion through space induced by the gravitational pull of nearby mass concentrations. By measuring the peculiar velocities of thousands of galaxies, Tully's team identified coherent flows where galaxies across enormous volumes of space were all converging in roughly the same direction. Laniakea is defined as the volume of space within which all galactic motions converge toward a single gravitational focal point called the Great Attractor, an immense concentration of matter, partly hidden behind the dense dust of the Milky Way's own galactic plane. This gravitational force pulls on everything within Laniakea, influencing galactic motion across hundreds of millions of light-years. The Milky Way, the local group, the Virgo cluster, and tens of thousands of other galaxies and clusters all converge toward the Great Attractor, forming an enormous gravitational drainage basin. 500 million light-years, a number that, however inert and abstract, remains hard to truly grasp. Imagine light traveling from one edge of Laniakea to the other, taking 500 million years to make the trip. When that light left, the most complex life on Earth was limited to simple marine organisms. Fish hadn't yet evolved. The Cambrian explosion, the rise of vertebrates, the age of dinosaurs, the evolution of mammals, and the emergence of human civilization all happened during the transit of a single beam of light across one and Laniakea isn't an isolated case. It borders other superclusters. The Perseus species supercluster sits adjacent to Laniakea. The Shapley supercluster, one of the most massive concentrations of galaxies in the nearby universe, sits roughly 650 million light-years away, exerting a colossal gravitational pull. Laniakea itself may be falling toward Shapley, part of an even larger flow that astronomers are still working to fully map. The hierarchy of gravitational structures doesn't stop at superclusters. It continues upward to the largest structures of matter distribution the universe contains. This is where the cosmic web reveals itself. If you could somehow step outside the universe and observe the distribution of all matter across billions of light-years, you wouldn't see galaxies scattered randomly through space. You'd see a vast interconnected network of filaments, walls, and nodes, resembling the structure of a sponge, the neural connections of a brain, or the arrangement of bubbles in foam. This network is called the cosmic web, and it represents the largest scale organization of matter that exists. The cosmic web is made of 4 kinds of structure. Nodes are the densest regions, intersections where multiple filaments converge. Galaxy clusters form at these nodes, anchored by enormous concentrations of dark matter. Filaments are long bridges of dark matter and gas stretching between nodes, often spanning hundreds of millions of light-years in length, while remaining only about 10 to 20 million light-years wide. Walls are vast flat surfaces where filaments intersect to form broad planar structures containing thousands of galaxies arranged in thin sheets. Between all of these structures sit enormous underdense regions, cosmic voids, where almost nothing exists at all. The filaments are the highways of the cosmos. Gas flows along them, channeled by dark matter's gravity, toward the nodes where galaxy clusters grow. Galaxies themselves preferentially form along the filaments, threaded like beads on a string. The material in the filaments isn't exclusively dark matter. Strands of ordinary gas, hydrogen and helium, run through these structures, heated to temperatures between 100,000 and 10 million degrees. This hot intergalactic medium had long been predicted by cosmological simulations, but it remained extremely difficult to observe, because its glow is too faint for most instruments to detect. That changed recently. In early 2025, an international research team using the MUSE instrument on the Very Large Telescope at the European Southern Observatory published an unprecedented high-definition image of a cosmic web filament connecting to galaxies at a distance corresponding to when the universe was roughly 2 billion years old. The filament stretched roughly 3 million light-years, and for the first time, researchers were able to directly trace the boundary between gas residing inside galaxies and gas contained within the cosmic web itself. Compared against state-of-the-art supercomputer simulations of cosmic structure, the observed filament matched theoretical predictions with remarkable precision. Later in 2025, a team of researchers at the University of Oxford identified one of the largest rotating structures ever observed, an extremely thin chain of 14 hydrogen-rich galaxies, embedded in a much larger cosmic filament, roughly 50 million light-years long, sitting roughly 140 million light-years from Earth. The galaxies within this thin filament were found to rotate in the same direction as the filament itself, far more often than chance alone would predict. This discovery challenged existing models of how galaxies acquire their rotational motion, suggesting the cosmic web may influence galactic rotation more strongly and on larger scales than previously believed. Meanwhile, the European Space Agency's Euclid telescope has set out to build the most ambitious map of cosmic structure ever attempted. Launched in July 2023, Euclid released its first batch of survey data in March 2025, covering 63 square degrees of sky and revealing 26 million galaxies in just its initial deep field observations. Within those fields, the large-scale organization of galaxies along the cosmic web was already visible, with clusters connected by filaments of galaxies stretching across billions of years of cosmic history. Euclid's mission will eventually map a third of the entire sky, measure the shapes of billions of galaxies across 10 billion years of cosmic time, and construct a three-dimensional map of dark matter distribution at scales never before achieved. The first major cosmological dataset is expected in October 2026. The structures revealed by these surveys are staggering. The Sloan Great Wall, discovered through the Sloan Digital Sky Survey, stretches roughly 1.4 billion light-years, making it one of the largest known coherent structures. It consists of thousands of galaxies arranged in a wall-like formation, spanning a significant fraction of the observable universe. Even larger is the Hercules corona borealis, Great Wall detected through the clustering of gamma-ray bursts, and estimated at roughly 10 billion light-years across. If confirmed at that scale, it represents a structure so immense that light would need more than a tenth of the current age of the universe just to cross from one end to the other. But structures only represent half the picture. The other half is the void. Cosmic voids occupy roughly 80% of the universe's volume. These enormous underdense regions, typically spanning 100 to 500 million light-years, contain almost no galaxies at all. They're the bubbles in the cosmic foam, the hollow spaces between filaments and walls, where matter has drained away under gravity's patient pull over billions of years. The Boat's void, discovered in 1981, spans roughly 330 million light-years in diameter and contains fewer than 60 known galaxies. If the Milky Way sat at the center of the Boat's void, the nearest major galaxy would be so far away it would appear as a faint smudge, detectable only with powerful telescopes. The night sky would be far emptier than what we see from our position in the cosmic web. The emptiness inside voids isn't absolute. Dark matter exists there at reduced density, forming faint filamentary structures too weak and too sparse to gravitationally capture enough ordinary matter for galaxy formation. Dark energy, which appears to maintain a constant density regardless of how much space expands, completely dominates the voids. With so little matter to resist expansion, voids grow faster than the cosmic average, swelling like balloons and pushing their boundaries outward into the surrounding filaments. This process has been ongoing for billions of years and will continue indefinitely. Voids grow, filaments thin. The contrast between dense and empty regions sharpens with time. The cosmic web is slowly dissolving, its delicate structure stretched by the relentless pressure of dark energy. The origin of all this structure traces back to the earliest moments after the Big Bang. In that initial fraction of a second, during the epoch of cosmic inflation, quantum fluctuations in the density of the primordial plasma were stretched to macroscopic scales. These fluctuations were extraordinarily slight, variations of roughly 1 part in 100,000, but they were enough. Regions of slightly higher density attracted slightly more matter through gravity. Regions of slightly lower density lost matter to their denser neighbors. This process amplified over hundreds of millions of years. Dense regions collapsed to form the first stars, which gathered into galaxies, which gathered into groups, which lined up along filaments. Underdense regions emptied further, expanding into voids. The cosmic web is the final product of gravitational amplification, acting on quantum noise for 13.8 billion years. The largest structures in the visible universe grew from the smallest fluctuations physics allows. The cosmic microwave background offers a glimpse of these fluctuations when the universe was only 380,000 years old. Satellites including COBE, WMAP, and Planck have mapped tiny temperature variations across the entire sky, revealing the seeds of all future structure. Warmer regions corresponded to slightly denser areas. Cooler regions corresponded to slightly less dense areas. Scientists feed this measured data into supercomputer simulations that model the interactions of gravity, dark matter, dark energy, and ordinary matter across billions of years. The resulting simulated universes produce cosmic webs that match the observed one with impressive fidelity. In the simulations, filaments form at the same scales and densities as real filaments. Voids open up at the same sizes and emptiness. Galaxy clusters appear at the nodes with comparable masses and temperatures. This agreement between theory and observation is one of the great triumphs of modern cosmology. We understand, in broad strokes, how the cosmic web formed and why it looks the way it does. But the agreement isn't perfect. Some observed structures appear larger or more extreme than simulations easily reproduce, if its size is confirmed. The Hercules Corona Borealis Great Wall pushes the limits of what standard cosmological models predict. Supervoids, like the KBC void, estimated at roughly 2 billion light-years in diameter, with a density deficit of about 20%, are rare enough in simulations that their existence raises questions about whether our models fully capture the entire range of cosmic structure. These tensions aren't crises, they're frontiers, places where observation pushes theory to evolve and improve. The cosmic web also serves as a laboratory for studying dark energy, the mysterious force driving cosmic acceleration. Because voids expand faster than average and clusters resist expansion through concentrated gravity, comparing the growth rates of different cosmic structures at different epochs lets scientists measure how dark energy's influence has changed over time. Euclid was designed precisely for this purpose. By mapping the evolving shapes and positions of billions of galaxies across the last 10 billion years, Euclid will help determine whether dark energy is a constant cosmological term, unchanging and uniform, or whether its strength varies across space and time. Either answer would be revolutionary. A constant dark energy confirms the simplest theoretical model, but leaves its fundamental nature unexplained. A variable dark energy demands entirely new physics that no current theory fully provides. Now consider the full extent of what the cosmic web represents. You began this journey on a planet 8,000 miles in diameter. You crossed a solar system whose gravitational boundary spans roughly 2 light-years. You crossed interstellar space to admire a galaxy 200,000 light-years in diameter. You expanded your view to the local group at 10 million light-years, to the Virgo cluster at 54 million light-years, and to the Laniakea supercluster at 500 million light-years. And now the cosmic web stretches before you in every direction, a tapestry of filaments, walls, clusters, and voids spanning billions of light-years, organized into patterns so vast that individual galaxies within them are smaller than points. Every galaxy ever photographed by the Hubble Space Telescope, every cluster mapped by X-ray observatorios, every supercluster identified through galaxy surveys exists as a minor element within this web. The Milky Way, the structure whose size occupied an entire portion of this story, is a single node in a single filament within a single supercluster, itself part of a network extending to the limits of what we can observe. The Virgo cluster, with its 1,300 galaxies and quadrillions of solar masses, is one node among millions. Laniakea, with its 100,000 galaxies, is one drainage basin among countless others. To fully grasp what just happened during this journey, consider the chain of containment, each link of which would have been incomprehensible to the occupants of the one before it. Earth is a planet orbiting a star. That star is one of 400 billion in a galaxy. That galaxy is one of more than 80 galaxies in the local group. The local group is a small structure moving toward the Virgo cluster. The Virgo cluster is one node among many in the Laniakea supercluster. Laniakea is one supercluster among millions in the observable cosmic web. Each structure contains the previous one the way an ocean contains a single drop of water, and at every step, moving from one scale to the next, rendered the previous scale invisible. Here's a way to feel the compression. If you represented the entire observable universe as a sphere the size of Earth, the Laniakea supercluster would be roughly the size of a mid-sized city within that sphere, about 70 kilometers across. The Virgo cluster would shrink to a few kilometers. a short walk through a single neighborhood. The local group would shrink to just over a kilometer, barely a few city blocks. The Milky Way would be the length of a swimming pool, and the solar system, everything humanity has ever physically explored, every spacecraft we've ever launched, every signal we've ever sent, would be smaller than a single bacterium. A bacterium inside a swimming pool, inside a neighborhood, inside a city, inside the Earth. That's the compression. Each level doesn't merely shrink the one before it, it annihilates it. The cosmic web accomplishes something no smaller structure can. It reveals the blueprint of the universe. The arrangement of filaments, walls, and voids isn't random. It's the direct, inevitable consequence of gravity acting on initial density fluctuations from the Big Bang, playing out across 13.8 billion years of cosmic evolution. Every thread in the web traces a line of slightly higher primordial density. Every void marks a region that initially held slightly less matter than its surroundings. The cosmic web is a fossil record of the quantum fluctuations that occurred during cosmic inflation, amplified from subatomic scales to structures spanning billions of light-years. It is the universe's autobiography, written in the language of gravity and time. The web is also a clock. Because light travels at a finite speed, observing cosmic structure at different distances means observing it at different ages. Nearby filaments and clusters show the web as it exists today. Distant images show what it looked like billions of years ago. By comparing the structure of the cosmic web across different epochs, astronomers can watch cosmic evolution in action. Filaments were denser in the past. Voids were smaller. Clusters were less massive. The web was tighter, more compact, less defined. Watching the web evolve over cosmic time is like watching frost crystals form on a window in time-lapse, except the window measures billions of light-years across, and the frost took 10 billion years to form. The Dark Energy Spectroscopic Instrument, DESI, is currently conducting the most ambitious three-dimensional mapping of the cosmic web ever attempted, precisely measuring the distances of tens of millions of galaxies and quasars. Its first results, released in stages starting in 2024, have already produced the most detailed picture yet of cosmic expansion's evolution over the last 11 billion years. Combined with Euclid's wide-field imaging and the James Webb Space Telescope's deep spectroscopy, these surveys are converging on a comprehensive understanding of how the cosmic web grew from primordial seeds into the vast structure we observe today. Every new survey reveals the same humbling truth. The structures we can see are immense, beyond comprehension, and they're contained within a volume that might represent only an infinitesimal fraction of the whole. And the cosmic web itself is contained within something, a boundary, not a wall or an edge, but a horizon imposed by the speed of light and the age of the universe. Everything we've discussed so far, from your footsteps to filaments spanning billions of light-years, exists within a finite volume of space, defined by the distance light has traveled since the universe began. Beyond that boundary lies a larger universe, potentially infinitely larger, that we have never seen and may never see. The cosmic web, in all its staggering immensity, is about to fit inside a single sphere, and that sphere may represent only an atomic fraction of what actually exists. The observable universe has a diameter of roughly 93 billion light-years. That sentence contains one of the most commonly misunderstood numbers in all of science, so it's worth unpacking carefully before going further. The universe is 13.8 billion years old. Light has been traveling since the cosmos became transparent to radiation, roughly 380,000 years after the Big Bang. You might reasonably expect the most distant thing we can see to sit 13.8 billion light-years away. but the universe has been expanding the entire time. Objects that emitted light 13.8 billion years ago were much closer to us when that light began its journey. During the billions of years that light spent traveling to Earth, the expansion of space carried those objects farther and farther away. By the time their ancient photons finally reach our telescopes, the objects themselves have been carried to a current distance of roughly 46.5 billion light-years. Double that figure to account for the opposite direction, and you get the total diameter, 93 billion light-years. The observable universe is far larger than the universe's age would naively suggest, because space itself stretched during light's journey. This observable sphere is centered on Earth, not because Earth is special, but because the observable universe is defined by the position of the observer. Every point in the cosmos has its own observable sphere, centered on itself, extending 46.5 billion light-years in every direction. An astronomer on a planet in the Andromeda galaxy would have a slightly different observable volume, overlapping hours in most places, but extending 2.5 million light-years farther in one direction and falling 2.5 million light-years short in the opposite direction. Every observer sits at the center of their own visible cosmos. This isn't a privilege. It's a geometric inevitability tied to the finite speed of light in an expanding universe. Within this sphere, current estimates place the total number of galaxies at roughly 2 trillion. This figure, published by a team using Hubble Space Telescope data combined with mathematical modeling, accounts for the many small, faint galaxies that fall below the detection threshold even of our most powerful instruments. Each of these 2 trillion galaxies contains anywhere from a few million to several trillion stars. Summed across the entire observable volume, the total stellar population comes out to roughly 10 to the 24th power. That's a septillion stars. Written out in full, that number is a 1 followed by 24 zeros. There are more stars in the observable universe than grains of sand on every beach, in every desert, on every ocean floor, across the entire surface of the Earth, and the pace of discovery keeps accelerating. In January 2026, astronomers confirmed that a galaxy designated Milky Way, discovered using the James Webb Space Telescope, is the most distant galaxy ever verified through spectroscopy. Its light reveals the universe as it appeared just 280 million years after the Big Bang, corresponding to a redshift of 14.44. The galaxy currently sits roughly 33.8 billion light-years from Earth due to cosmic expansion over the intervening eons. Milky Way 4 is brighter, more compact, and chemically richer than theoretical models predicted for galaxies forming so soon after the universe's origin. Its existence, along with roughly 100 times more luminous primordial galaxies than standard cosmology predicted, suggests star formation in the early universe was far more vigorous and efficient than scientists had imagined. The James Webb Space Telescope hasn't just pushed the limits of observation. It has revealed that the early universe assembled complex structures at a pace that challenges the models built to explain it. The farthest boundary of our observable volume isn't marked by distant galaxies, it's marked by a wall of light. The cosmic microwave background is the oldest electromagnetic signal in existence, emitted when the universe had cooled enough for the first stable atoms to form. Before that moment, the universe was an opaque fog of plasma, so hot and so dense that photons could travel only microscopic distances before being scattered by free electrons. When atoms formed and electrons settled into orbits, the fog cleared. Light could suddenly travel freely, and it has been spreading through space ever since. This primordial light now reaches us from every direction, stretched by 13.8 billion years of cosmic expansion into microwave wavelengths at a temperature of roughly 2.7 to 5 degrees above absolute zero. It is extraordinarily uniform. In every direction astronomers look, the temperature is the same to within a few hundred thousandths of a degree. This uniformity tells us the early universe was almost perfectly smooth, with only the faintest density variations from quantum fluctuations during inflation. These ripples, mapped with exquisite precision by the Planck satellite, encode the initial conditions from which all cosmic structure eventually grew. Every galaxy, every cluster, every filament of the cosmic web traces its origin back to the pattern of infinitesimal temperature variations in the cosmic microwave background. The cosmic microwave background also imposes an absolute observational limit. No electromagnetic telescope can see beyond it. Before the universe became transparent, no light could travel freely, so no image of earlier epochs can ever be captured using photons. The first 380,000 years of cosmic history are hidden behind this wall of ancient radiation. Other observational windows might eventually pierce this barrier. Gravitational waves generated during inflation could carry information from even earlier instants. Neutrinos decoupled from matter roughly 1 second after the Big Bang, far earlier than photons, and a cosmic neutrino background should exist, though detecting it remains beyond current technological capability. For now, the cosmic microwave background is our deepest glimpse into the past, a newborn portrait of a universe barely emerged from its primordial state. Beyond the observable universe lies a larger universe still. Exactly how much larger is a question current physics can constrain, but cannot definitively answer. The most rigorous approach uses measurements of the cosmos's spatial curvature. If the universe is curved like the surface of an enormous sphere, very distant triangles drawn in space would have angles summing slightly more or less than 180 degrees. Depending on whether the curvature is positive or negative. Measurements from the Planck satellite show that space is flat, to the precision of our instruments. This flatness implies the universe is either infinite or vastly larger than the observable portion. Statistical analyses based on Planck data suggest the total universe has a radius at least 250 times larger than the observable volume, corresponding to a minimum diameter of roughly 23 trillion light-years. If this lower bound is correct, the observable universe occupies less than 1 part in 15 million of the total cosmic volume. For every galaxy visible to us, there exists at least 15 million more beyond our horizon, and that's a conservative estimate. The true universe could be considerably larger still, or even infinite. That possibility demands a moment of serious thought. If the universe is infinite, it contains an infinite number of galaxies, an infinite number of stars, and an infinite number of planets. In an infinite cosmos where physical laws and constants are uniform, every physically possible configuration of matter must occur somewhere. This includes configurations identical to our own solar system, our own planet, our own civilization. In a truly infinite universe, there must exist regions of space where the arrangement of atoms exactly mirrors the conditions that constitute you right now. The implications of infinity aren't merely strange, they're dizzying. They challenge the very concept of uniqueness. If everything that can happen does happen somewhere in infinite space, then nothing is truly unique, not even you. Whether the universe is infinite or simply unimaginably vast, the portion beyond our observable horizon remains permanently inaccessible. This isn't a technological limitation. It's a limitation imposed by the laws of physics themselves. The universe is expanding, and that expansion is accelerating. In 1998, two independent teams studying distant type EAA supernova discovered that the expansion of the universe isn't slowing down under gravity, as most physicists had expected. It's speeding up. Something is pushing space apart with increasing vigor. This something, called dark energy, for lack of a better term, constitutes roughly 68% of the universe's total energy content. Dark matter accounts for roughly 27%. Ordinary matter, the atoms and molecules that make up stars, planets, and people, accounts for roughly 5%. The universe is overwhelmingly composed of substances we can detect only through their gravitational effects, whose fundamental nature remains one of the deepest unsolved problems in physics. Dark energy's acceleration carries a consequence that unfolds across cosmic time with quiet but devastating finality. Galaxies beyond a certain distance are currently receding from us faster than light. This doesn't violate Einstein's relativity, because the galaxies aren't moving through space faster than light. Space itself is expanding, carrying them along. But the practical result is identical. Light emitted today by those galaxies will never reach us. They sit beyond our causal horizon. We cannot observe them, communicate with them, or be influenced by them in any way. And the number of galaxies crossing this threshold grows with every passing moment. Accelerating expansion is steadily shrinking the number of cosmic neighbors we will ever be able to physically interact with. In roughly 100 billion years, if dark energy continues behaving as current measurements indicate, every galaxy beyond the local group will have receded past the cosmic event horizon and become invisible through redshift. A civilization emerging in that distant future would see, in the sky, only the merged remnant of the Milky Way and Andromeda, a single giant elliptical galaxy surrounded by a handful of gravitationally bound satellites. Within another trillion years, even the cosmic microwave background would have stretched to a wavelength too long for any conceivable instrument to detect. The evidence for the Big Bang, for cosmic expansion, for the existence of other galaxies, would have vanished entirely. Those future astronomers, however brilliant, would have no observational basis for concluding that a larger universe ever existed. They would live in a cosmic dark age, isolated within a single galaxy, the true nature of the cosmos, hidden from them forever by the very expansion of space itself. It happens that we exist during a brief window of cosmic history when the evidence is still visible. The cosmic microwave background still glows faintly in our instruments. Distant galaxies still send photons that reach our detectors after journeys of billions of years. The large-scale structure of the cosmos remains visible in galaxy surveys and gravitational lensing maps. We can still piece together the history. This window of opportunity won't last, at least not on a cosmic timescale. The universe is slowly erasing its own history, removing the evidence one galaxy at a time, making it permanently inaccessible. Now step back and consider the journey as a whole. You began this story as a 5.5-foot silhouette on the surface of a planet roughly 8,000 miles in diameter. That planet orbits a star 93 million miles away. That star is one of 400 billion stars in a galaxy 200,000 light-years across. That galaxy belongs to a local group of more than 80 galaxies, spanning 10 million light-years. That group belongs to a cluster of more than 1,000 galaxies sitting 54 million light-years away. That cluster sits within a supercluster spanning 500 million light-years. That supercluster is embedded in a cosmic web of filaments and voids stretching billions of light-years. And all of it, every filament, every void, every galaxy, every star, every planet, every atom, exists within an observable sphere, 93 billion light-years in diameter, which might represent less than 1/15 millionth of the total universe. Every one of these steps followed the same pattern. A scale that seemed unbelievably large turned out to be insignificant inside the next one. The solar system, which our fastest spacecraft have spent decades only partially crossing, vanished into a single point within the galaxy. The galaxy, with its hundreds of billions of stars and trillions of solar masses, became a single point of light within the local group. The local group dissolved into a minor element of the Virgo cluster. The Virgo cluster shrank to a single node among millions in the cosmic web. And the cosmic web, the largest structure we can map, fits inside an observable volume that may itself represent only an atomic fraction of everything that exists. This is the fundamental truth about cosmic scale. And it's more radical than simply saying the universe is large. The universe keeps putting us in our place. Every frame of reference you adopt, however vast, turns out to be a tiny detail within a larger frame you haven't yet accounted for. There's no scale at which you can stop and say, now I've reached the level that matters. Every level is simultaneously enormous from below and insignificant from above. The solar system is immense beyond human experience and insignificant on a galactic scale. The galaxy is colossal beyond galactic experience and invisible on a cosmic scale. The observable universe is the largest thing we can measure, and it might represent only a tiny fraction of what exists. It's this recursiveness that distinguishes the true scale of the universe from mere bigness. A large number is just a large number. You can read it, write it down, and move on. But the systematic collapse of every scale into the next produces something more unsettling. It reveals that human intuition isn't merely slightly miscalibrated for the cosmos. It's fundamentally, structurally, irreparably inadequate. Our brains evolved to navigate a world of footsteps and throwing distances. With some effort, we can stretch our intuition to encompass continents and oceans. Beyond that, the numbers become abstractions. The distance to the moon is a number. The diameter of the galaxy is a number. The size of the observable universe is a number. But none of these figures correspond to any physical sensation your brain can generate. You can't feel the void between galaxies. You can't perceive the curvature of cosmic filaments. It's impossible to intuitively grasp the 14 billion year journey of a photon from the cosmic microwave background. These numbers exist in your mind as pure data, disconnected from experience, with no link to anything your body has ever encountered. And yet here you are, a temporary assembly of atoms on the surface of a small planet, orbiting an ordinary star in the suburb of one galaxy among 2 trillion. Your body is built from elements forged inside stars that exploded before the solar system even existed. Every atom in your body heavier than hydrogen was manufactured inside a star that no longer exists. Those atoms were expelled into space by explosions and stellar winds, drifted through interstellar clouds for millions of years, and were eventually gathered by gravity into the collapsing disk of gas that became our solar system. You don't simply come from the universe. You are the universe, reorganized into a pattern that became capable of contemplating itself. Matter that became aware of matter. Complexity born from simplicity across billions of years of cosmic time. This isn't a sentimental observation. It's a physical fact. The same laws of physics that govern the expansion of cosmic voids and the collapse of galaxy clusters also govern the electrochemical signals firing in your neurons as you process these words. Gravity shaped the cosmic web. Nuclear fusion forged the elements. Chemistry assembled the molecules. Biology organized the cells. And consciousness emerged from that biological complexity. a phenomenon so improbable that we've found evidence of it in only one place in the entire observable universe. And yet it's powerful enough to reconstruct the history of that universe from fragments of ancient light. A species that evolved 70,000 generations ago on a patch of African savanna has built instruments capable of detecting photons 13.5 billion years old. It has mapped the distribution of invisible matter across billions of light years. It has photographed the shadow of a black hole in another galaxy. It has measured the faint glow of the primordial fireball that filled the universe before a single star existed. It has landed machines on other worlds, detected gravitational waves from colliding neutron stars, and confirmed that the expansion of the cosmos is accelerating under the influence of a force it doesn't yet understand. That last point is worth sitting with. We don't understand 68% of the energy in the universe. We can't directly detect 85% of the matter. We can observe only a small fraction of the total cosmic volume. Our best theory of particle physics is incomplete. Our best model of cosmic evolution contains parameters we measure but can't derive from first principles. By any honest accounting, we remain deeply ignorant of the fundamental nature of the reality we inhabit, but we know more today than we did yesterday. The Euclid telescope is building the largest three-dimensional map of cosmic structure ever assembled. The James Webb Space Telescope is pushing the boundaries of observation toward the era of the very first stars. The Dark Energy Spectroscopic Instrument is measuring the universe's expansion history with unprecedented precision. Gravitational wave observatories are opening entirely new avenues for cosmic observation. Each of these instruments will refine our understanding, correct our mistakes, and reveal new layers of structure and complexity we haven't yet imagined. The true vastness of the universe doesn't diminish human significance, as is so often assumed. The common reaction to cosmic scale is a feeling of helplessness. We are small, therefore we don't matter. But that conclusion doesn't follow from the evidence. Smallness is a spatial measurement. Significance is not. A single human allele carrying a mutation that alters the course of evolution is microscopically small and biologically pivotal. A simple equation written on a chalkboard can redirect the technological trajectory of a civilization. The relationship between physical size and cosmic importance isn't linear, the way our intuition suggests. The universe doesn't grant significance based on volume. What the true scale of the universe actually reveals is something more nuanced and more extraordinary. It reveals that the cosmos is structured in such a way that, across billions of years and billions of light years, organized complexity could emerge from initial simplicity. Quantum fluctuations became cosmic structure. Hydrogen became stars. Stars became heavy elements. Heavy elements became rocky worlds. Chemistry became biology. Biology produced minds capable of reconstructing this entire chain of events from observations made on the surface of a small planet. The immensity of the universe isn't a statement about humanity's insignificance. It's a statement about the depth and richness of the physical processes that produced us. The journey from quantum noise to conscious observation required every one of those billions of light years, and every one of those billions of years. This immensity isn't incidental. It's the mechanism. You are sitting on a rock 8,000 miles in diameter, orbiting a star that is one of 400 billion stars inside a galaxy that is one of 2 trillion within an observable volume that might represent 1/15,000,000th of the total. Every scale you thought was the largest turned out to be a rounding error inside the next one. The numbers are real. The distances are physical. And none of it, not a single light year, is wasted. Because somewhere within this incomprehensible expanse of space and time, the universe accomplished something no amount of emptiness can diminish. It woke up, looked around, and began measuring itself.